Hey class, today we're going to be discussing matter and its classification and how we can organize different types of matter. And this is kind of a natural thing. We saw that in class we talked about how humans naturally want to organize things based off similar characteristics. And so we're going to try to do the same thing with matter. And as you see right here, I have uh, the chart, if you want to call it a flow chart, or if you want to call it a diagram, you will, of the organization of matter. I call this the organization of matter chart, and it's a good way to look at it. Well, it's the correct way to look at it, really. So when we get down to it, we have to ask, well, what is matter? And all matter is anything that has mass and takes up space. That's kind of the definition that we've known since junior high. Anything that has mass and takes up space. That's what matter is. When you get down to the nitty-gritty of it, though, matter is just a collection of atoms. And how those atoms are and how they're arranged determines the type of matter. And so we know that atoms are the smallest divisible particle that retains its chemical properties. So we know that there's an atom, and then an atom has the nucleus on the inside and the electron cloud on the outside, and the nucleus contains protons and neutrons, and the outside contains these electrons. And that kind of tells us that, uh, hey, every atom has these combinations of protons, neutrons, and electrons. And the different combination of protons being the most important is what kind of makes it a different atom. So the hydrogen atom will have one proton in its nucleus, while the nitrogen atom will have 7 protons in its nucleus. That's what makes them different. Sure, they have different neutrons and they have different electrons also, but the key part there is they have different number of protons. So when we go through that periodic table, you look through and you'll see, oh, so this element has, sodium has 11 protons, or uh, neon has 10 protons, or and you go down there and you look through it and you see that they have the number of protons determines the type of atoms it has. And then the types of atoms that are present and how those atoms are arranged determines what kind of matter it is. So when we are trying to understand the organization of matter, we first need to understand that it starts from the atomic level first and foremost. And so that's why I have this down here. So if you look down here, we're going to look at atoms of matter. So look over here, and I have my first line here is that if I have atom 1 and atom 2, and I combine atom 1 and atom 2, and for this instance of hydrogen and hydrogen, it's the same thing. You see that this hydrogen and this atom, which is hydrogen, and this atom, which is hydrogen, when they combine to form H2, they form an element. Well, why do they form an element? They form an element because it's the same atom. It's the same kind of atom throughout. That's what makes it an element versus a compound, which we'll see in a second. So go down to the second line right here. If we look down here at the second line, we have 2 atoms here again. But this time the atoms are hydrogen and now they're oxygen. And when they combine in a specific kind of way, you get H2O, you get water. And we're familiar with water. Well, water isn't an element. It's a combination of elements. It's the combination of the atom hydrogen and the atom oxygen. And when I get 2 of the atoms of hydrogen and I get 1 of the atoms of oxygen, I'm going to they're arranged in a specific arrangement. They're going to form the compound water and the molecule water. Now, in class, we've discussed that this is ultimately what makes something an element versus a compound. And so in class, you've seen me draw the diagram of the cup. And so I'm going to draw my little 5 cups that I have done in class, and I'm going to illustrate this point again. So in class, we have our 5 cups here, and 1, 2, 3, 4, 5. So in our first one, we're going to have H2, H2, H2. Was there anything other than H2 in this cup? Anything other than H2 in this little canister? So there's only one thing. It's H2. There's there's one substance in here, and it's H2. That makes this substance in here a pure substance because it's purely H2. It's purely H2. And it's also an element. So it's a pure substance that happens to be an element. You combine that, and we have, in another canister, you have O2, 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 and O2. If you look over here, it's also uniformly throughout. That is uniformly oxygen. There's nothing other there than O2 and O2 and O2. That makes this a pure substance also. Well, what kind of pure substance? Well, do I have anything other than oxygen? No. Any other atom other than oxygen present? No. So that makes that an element. Just like this over here was an element. Now, what happens if I were to mix this H2 and this O2, and I were to combine them chemically? Now, I'm going to say that phrase again. If there was a chemical reaction and H2 atoms or hydrogen atoms were to bond or combine chemically with oxygen atoms in the ratio of H2O, H2O, and H2O. Now, I know that this is not mathematically correct. I understand stoichiometrically speaking that this isn't correct. But this is just for an example. So those farther along in their chemistry journeys, don't berate me, please. Well, if we look at this canister now, do we see anything other than H2O, H2O, H2O? No, it's uniform. It has one form, because the word uni means one, and one composition throughout. That's form. So it has a uniform composition, which is a makeup. And that uniform composition happens to be H2O. But do I have more than one kind of atom represented here? I do. I have two kinds of atoms. And when they are chemically bonded, two types of atoms are chemically bonded, they are compounded. This makes it a chemical compound. And since it's the same chemical compound all throughout, I also have a pure substance. So let's go back to our little chart here, and we have the organization of matter. Let's try to move that out of the way. Let's reduce that toolbar. So I have the organization of matter here. And matter is broken down into two things. It's broken down into whether you're pure substance and a mixture. But a pure substance is either going to be an element or a compound. If it's only one kind of atom throughout, one kind of atom throughout, it's going to be an element. If there's two or more that are chemically bonded and they are the same throughout, it's going to be a compound. I hope that makes sense as far as a pure substance goes. Okay, now let's go back to our five little cups over here. Now, what if, since this is not in the correct ratio of H2O, that I have a total of 6 hydrogens here, and I have a total of 8 oxygens here. Well, mathematically speaking, you notice that I used up all my hydrogens over here, and I only used up 3 out of my 8 oxygens here, right? There's 2, 4, 6 hydrogens here, 2, 4, 6 hydrogens, and there's only 3 oxygens, and I had 8. So that means I have 5 oxygens still floating around in this canister if I wanted to be mathematically correct. So I come over here and I draw I'm going to go ahead and draw my canister again so I can make it fit better. So here's a bigger canister. So I'm going to draw my 3 waters, H2O, H2O, H2O. And then I'm going to draw, I have 5 left, so that's 2 oxygens, 4 oxygens, and I'm going to have another one floating around here. Or let's make that ozone. There, let's make that ozone. There we go, O3. So how many different things do I have present? This is one chemical compound. This is an element. Oh, this is another element, it's the ozone. So I have 3 different substances contained in this mixture, and they're not chemically bonded. Well, how do I know they're not chemically bonded? The way I know they're not chemically bonded is because when you look at this, the arrangement of letters and numbers, so let's look at this H2O here. You see how they're close to each other. There's no space in between them. So it's H subscript 2O, and there's not a space in between them. That's letting me know that they're chemically bonded, as opposed to, so let's take something that we're maybe familiar with, is sodium chloride. If I take NaCl, you see how they're close to each other? That means it's a compound. But if I were to take sodium ions, a space leave between there, and chlorine ions, well, they're not bonded. They're separated from each other. So you come back over here, and you see how this O2 is kind of off to the side over here. This O2 is separated from this hydrogen, and I have this O3 that's kind of hanging out over here. And so I have three different species, if you will, of compounds or groups here. I have an oxygen, an ozone, and a water. And they're just all hanging out together. And above all, they are not chemically bonded. That's the most important part, is that they're not actually chemically bonded. Since they're not bonded, they're just hanging out together, they're mixing about together, that's going to be called a mixture. Okay? That's what a mixture is. So in this one right here, I have a mixture. Now, well, we actually won't use this last one. I think we kind of got the point here that this is the difference between a pure substance and a mixture. And in pure substances, I have an element and a compound. And then in mixtures, I have, well, there's two different kinds of mixtures that we see here. So this is where we've gotten to in class so far, is discussing this element and compound. And then we discuss mixtures. But now we need to get into these two new phrases. Homogeneous, as you can see, homogeneous right here, homogeneous, and heterogeneous. Two new phrases. And so what do they mean? And what kind of determines whether something's a kind of a homogeneous mixture or a heterogeneous mixture? And it's actually pretty easy. Homogeneous mixture and heterogeneous mixtures are really just mixtures based off of size. It's how big the particles are that are mixing together. So, and it's similar to and sometimes the homogeneous mixture can be confused for a compound. Right here. They can be confused, and they're not the same thing. But we just can't see with the naked eye that they're not the same thing. So let me take, for example, here. Say I have I have another canister, and it's filled with water, right? And I've poured table salt into the water, and it's gone here now. And the table salt's in there now, and the table salt now is mixed evenly throughout. I can't tell if there's any sodium chloride there. So not only is there H2O in here, and sodium chloride was poured in, now I can't tell. And then I know that the water broke apart the sodium and chlorine. So not only do I have water in here, I also have sodium ions, and I have chlorine ions. But we know that we can't see that with the naked eye. So it looks the same throughout. So this canister looks like it's just pure water. I can't tell with the naked eye that it's not pure water. Why can't I? Because the things that are being mixed in are so small that I can't tell the difference, so it looks the same. I keep saying the word same over and over again. That's because that's what the word homogeneous means. Homogeneous. The prefix there is homo, which means same. So in a homogeneous mixture, the particles, or what's being mixed, is so evenly mixed together that you can't tell the difference, and it looks like it's one. It looks like it's a pure substance, but it's not. Okay? So we call that, and if I want you to look at this line, that there's only one line coming down from this, and that's called a solution. So we call that all the time. And a lot of times in chemistry, we have a solution of a water and an acid. When we want to, if we have a pretty strong acid, like so today we took the sulfuric acid. We took H2SO4, and it was a pretty high concentration. So it was mostly H2SO4. Let's just assume it was pure H2SO4 in this canister. Okay, so we had this thing of H2SO4 acid. Okay. But 18 molar, the concentration is 18 molar, that is very dangerous. That can burn, hurt you really bad. And so we don't want to have that much. And so you take your stock supply, and so it can go farther, you dilute it, like you do with pretty much anything else. You dilute it, and so you dilute it by putting more water into it now. And so now you pour water into it. And no longer is it just sulfuric acid. It is now a combination of sulfuric acid and H2O. The moment it stops being purely sulfuric acid and now it's mixed with H2O, I now have H2SO4 and I have H2O, and I honestly have some hydronium also. So I have some other things in there too. Are they mixed? Yes, they are. They're mixed. But can you tell? No, because they are mixed on the molecule level, molecular level. So think of it like particles. You can see boulders, and you can see smaller rocks, and then you can see grains of sand, but you can't see anything smaller than that, or when you get to the micro size, or due to the molecule size that you can't see. When things are mixing at the very smallest level, that's called a solution. It's in a homogeneous mixture. That's why it does look the same, is because you can't see the difference. And that ultimately is the difference between a homogeneous mixture and a heterogeneous mixture. They are both mixing. They're not chemically combining. But in a homogeneous mixture, they're mixing so small, the things that are actually mixing are mixing so evenly because they are so small that you can't tell the difference, and so it's called a solution. So remember this phrase, that when I say the word homogeneous mixture, it can be used interchangeably with solution. And as you can see right here, let's focus again, homogeneous mixture and solution are the same thing. So the second part of that is then the heterogeneous mixture. And there's two types of heterogeneous mixtures. And that is going to be a colloid and a suspension. And I want you to think of it like this. I want you to think of it as particle size, okay? Think of it like a particle size spectrum, where when particles are the smallest mixing together, roughly on the nanometer scale, that's going to be a solution. When it gets bigger by factors of 1,000, so if it gets 1,000 times bigger to the micrometer stage, and that's the medium, right? We agree that's kind of medium. Well, sometimes you can see it with your naked eye, or if not naked eye, then you can see it with a laser or something, but it's still your naked eye. That's called a colloid. Is it the same throughout? No, it's not. That's why it's not a homogeneous, because the particles are just barely big enough where they're not evenly mixed throughout. If you want to think of something, think of smoke. Smoke is kind of a good idea. Smoke is a good thing to think about. Or think of whipped cream or something where you can see the air pockets in there. The particles are really small, but you can see the difference between the air and the solid there. And the last one is the suspension, and that's the most obvious one. That's where the particles mixing are the largest. And this is so anything bigger than 100 micrometers, so anything getting close to a millimeter in size, mixing together, is going to be a suspension. And that just means that they are suspended together. So when we think of a colloid or a solution, think of an acid mixing together. It's so tiny you can't see it. When you think of a colloid mixing together, think of like an aerosol can, where you have particles of air mixing with a liquid, but you can just barely tell that there's two different phases there involved. So there's a liquid phase and a solid phase. And then finally, the largest of the mixtures mixing together is the suspension, and that's almost everything we can see around us. So think of cereal as the best example, right? So I take my milk and I take my corn flakes, or my Fruity Pebbles, which are the best cereal, of course. We all agree that Fruity Pebbles are the best. And I mix them in there together. I can clearly see the milk, and I can clearly see the Fruity Pebbles. That's a suspension. The Fruity Pebbles are suspended into the milk. Or think of a river. Think of the Mississippi River or the Missouri River. And you see the silt there floating through. That's a suspension. So in a colloid, so the largest particles are a suspension. The second largest, or second smallest, if you will, is a colloid. It's kind of a medium-sized thing, and and when I say they're small, I mean, there doesn't seem like a whole difference between a nano and a micro, but there's 1,000 times bigger difference. So that is a big difference. But anything after 100 micrometers, anything after that, getting close to the millimeter range, from the smallest grains of sand to huge boulders, those are all suspensions. So the colloid one is the one that's kind of the most confusing, because it's sometimes hard to tell which one is the difficult one. Just to forewarn you, if you're watching this video, this will help you out. Blood is a colloid. Well, why is that? Well, because inside blood we have not only we have our plasma, so I have blood here. Let's actually make this. Let's make this red. So I'm gonna draw some blue lines. Those are gonna be my blood vessels. Okay. Then I'm gonna draw some red blood cells. And blood cells are micrometers, several hundred micrometers, 60 or so micrometers big. So I have these little biconcaved blood cells that are floating through. Not only that, then I have some larger proteins there. And then I have plasma, which is mostly water there floating throughout. And then I have my white blood cells that are floating throughout. So we can see then that, let's go get it here. I have my white blood cells. And if I spin it apart, if I take blood and I spin it, guess what? Through a centrifuge, I'm going to separate that plasma from the red blood cells. The sheer size of the blood cells alone make this a colloid. To us, to our naked eye, we think it's a solution, but it's really a colloid. So I hope this clears some things up. Some things I'm going to hit up later in class, though, that I actually haven't mentioned. If you notice these three things that I didn't mention right here, under compounds here, there are just different kinds of compounds, how they're formed, and it's not actually part of this chapter, but it is good to know that a compound can be formed ionically. So if it's formed ionically, it's an ionic compound. It can be formed covalently, and if it's formed covalently, it's a covalent compound. And if it's formed with metals, it's a metallic compound. And if you want to know the easiest way to figure that out, it's really nothing special. If it's a metal mixing with a non-metal, it's going to be an ionic compound. So if you look right here, let me erase all this right here, and we can go to this part right here. If I have a metal and it has to chemically bond with a non-metal, it's going to form an ionic compound. A covalent compound is going to be between a non-metal and another non-metal. And the periodic table is mostly metals. If we look at it, we have the alkali metals, alkali earth metal, transition metals. That takes up a good 3/4 of the entire periodic table of elements. So we have a lot of opportunities for ionic compounds, but we have a whole lot of covalent also, so ionic covalent. And the metallics are metal and metal. That's some nice juxtaposition there. So again, there's one quick review again. So matter, there's two types of matters, a pure substance and a mixture. The pure substance are things that are uniform throughout, and they can either be an element or a compound. Elements is made up only one kind of atom. Compounds are chemically bonded to or more different kinds of atoms in different ratios. And those compounds can form ionically, covalently, or metallically. Over here, when things aren't chemically combined, but they're still physically touching each other, it's called a mixture. And you have a homogeneous and heterogeneous mixture. And they're basically based on size. If it's really, really small things that you can't tell the difference between it, it's a homogeneous mixture called a solution. If it's larger things, almost even barely above the naked eye and up to the obvious naked eye that are mixed together, it's a colloid dense suspension. I hope that makes sense to everybody, and if you have any questions, I'd be glad to help you out. Thank you.